Hi, welcome to today's session on finding the linear nth term rule. So we use the linear nth term rule to try and predict other numbers within a sequence, or maybe to generate a sequence. But when we've got a sequence in itself, we are looking to actually find a rule that would suit this sequence. So here we've got a sequence of 3, 5, 7, 9, 11. And what we're looking to do is trying to create or find the nth term rule for this sequence, where we could predict other numbers within this sequence. So each one of these numbers has a term position. They have their position within the sequence. So 3 is my first term, 5 is my second term, 7 is my third term, and so on and so forth. Whenever we're talking about just straightforward nth term, we're not talking about quadratic nth terms, in which case when we create our nth term rule, there's going to be no powers in there, there's going to be no indices. Though when we're looking at those, we'll actually look at those within when we're talking about quadratic nth term, and also when we're talking about geometric sequences. So to find the linear nth term rule for this sequence here, first of all, I'm going to show it using the Dino method, and then I'm going to show it using a more linear method. So di here is the difference, n is just little n, and o is not o, it's actually 0. It's going to be the 0 term. So here's the same sequence. Now the first thing was the di, the difference. So the difference here, going from 3 to 5 is 2, 5 to 7 is 2, and it continues. So it's plus 2 each time. It's a positive 2, so I'm just going to write 2 underneath my di. My n is going to come straight down, and now I'm going to look at my o. So I've got my first, second, third, fourth, fifth term. I'm looking for my 0 term. If I'm adding 2 each time going this way, to go this way, I'm going to subtract 2 from my 3, which gives me positive 1. Because it's positive 1, I'm going to write plus 1 underneath my o, in which case that is now my nth term rule, 2n plus 1. Now, anytime that you're asked to maybe find or generate the nth term rule, it could also ask for the expression. This is the exact same problem because those of you who know your algebra, an expression is just a sum without an equal sign there. Now I'm going to show it using the linear method. So again, got the exact same problem, in which case we know that the n answer that we should come up with is 2n plus 1. So first thing I'm going to do, I'm just going to write n to one side. Going to take the exact same first step, find the difference between my numbers. How do I get from one number to next, to next, to next, to next? And it's a constant plus 2. It's a positive 2, so I'm going to write a positive 2 in front of my n. Now, bear in mind that this is 2 times n, and n is actually just the position in the sequence. So underneath each one of my terms down here, I'm actually just going to write my 2 times table. Just for the first 5 terms of my 2 times table, because 2 times 1 gives me 2, 2 times 2 gives me 4, 2 times 3 gives me 6, 2 times 4 gives me 8, 2 times 5 gives me 10. Now, the next thing I'm going to do is look at how do I get from 2 to 3, how do I get from 4 to 5, how do I get from 6 to 7, and so on and so forth. Is there a constant additional subtraction from 2 to give me to my 3, and which works for all the rest of the terms? Here you can probably see, to get from these numbers to these numbers, I add 1 each time, in which case that is a constant addition, in which case this add 1 I just literally put on the end of my 2n, and again we've actually created the rule for this. We've created our 2n plus 1. Now for some of you this might work a lot easier. For others, the Dino method might be more of a more straightforward way to do it. Whichever way works for you. I'm now going to actually test this rule just to see if it works. another way of being able to check my answers. So I know my fourth term is 9 because 1, 2, 3, 4, my fourth term is 9. So if I took my m term rule now and replaced my n with the number 4, because remember this n is just my position number in my sequence. Replacing that with 4, I've got 2 times 4, which is 8. Add the 1, it certainly does give us 9. So we know that just by checking this, that this works for the fourth term. We could actually use this to predict other numbers in the sequence. So let's say I'm looking for the 50th term. If I was to replace my n with 50, because I'm looking for my 50th position term, 2 times 50 is 100. Add the 1, that certainly is 101. So my 50th term would be 101. Now, not all sequences are going to be increasing as they go up. Some of them are going to be decreasing, and some of them could involve negative numbers. So here we've got 7, 5, 3, 1, minus 1, and then it's an infinite sequence because it goes on, as shown by these 3 dots. Again, just putting my position numbers underneath each, and I'm going to use the Dino method to find my nth term rule for this sequence just here. So my difference is subtracting 2 each and every time. So because I've got a negative 2, I'm going to write a negative 2 underneath my di. N comes down, and I'm going to find my 0 term. I'm subtracting 2 going this way, so to go this way, I'm going to add 2 to my 7, which gives me 9. Because it's a positive 9, I'm going to write plus 9 underneath my 0. So my nth term rule is minus 2n plus 9, or negative 2n plus 9. Again, just showing that it does work with the linear methods as well. Got the exact same sequence. So starting off by writing my n, I'm going to write my 2 times table, sorry, I'm going to find my difference, which is minus 2 each time. So now I've got negative 2 in front of my n, so I'm actually going to do my negative 2 times table. So minus 2 times 1, that gives me minus 2. Minus 2 times 2 gives me minus 4, and so on and so forth. I'm going to do the exact same method where I'm going to look how to get from these numbers to these numbers. And each time, to get from minus 2 to 7, I've got to add 9. To get to minus 4 to 5, I've got to add 9. And it works for all the rest of them. So I just plug this plus 9 onto the end of my minus 2n, and that has again gave me my nth term rule. And of course, this could be tested. So if I replace my n with 4, I know that my fourth term should be 1. And minus 2 times 4 gives me minus 8. Plus 9, that certainly does give us 1. And again, we could find our 50th term. So again, minus 2 times 50, that will give us minus 100. Add the 1, give us minus 99. So our 50th term in this sequence would be minus 99. If you like what you see, please subscribe. Thank you very much for watching.